Yes.
Yes, Michael.
All right. Yes. My name is Michael Andersen, and I'm going to give a presentation about my PhD work on bridge aeroelasticity and the non-flutter design principle for long-span bridges. I will shortly introduce the subject before we move on to the topics I dealt with during my research, and this includes a number of case studies on suspension bridges, would focus on the influence of span length, mass, and stiffness properties on the aerodynamic stability of the bridge girder. So also a large part of my work was dedicated to study the influence of the cross-sectional shape on the aeroelastic properties of long-span bridges. But the main research question I've been working on to answer concerns the non-flutter design principle and whether it's possible to construct lightweight bridges by reducing the torsional lateral frequency in order to avoid coupled vertical and torsional flutter, which is also known as classical flutter. Flutter is basically a aerodynamic instability where the mutual interaction between the incoming wind and the bridge deck and the flow around and behind it creates a situation where the effective damping of the total system becomes negative. We all know classical single degree of freedom system where you have positive damping and you give it a initial displacement and you'll see a free decay. If you did this for this coupled fluid structural system having negative damping instead of decaying motion, you would see diverging motion, which is basically the definition of flutter. Well, flutter can be either damping driven or stiffness driven. For flat plates or streamlined bridge decks where we have positive torsional aerodynamic damping, it's mainly stiffness-driven flutter we are concerning with. But for more bluff cross-section, we can experience torsional flutter, which was... Hi. Skal I bruge lokalet? All right. Yeah, sorry. Yeah, for more bluff cross-sections like the Tacoma Narrow cross-section, we will experience torsional flutter. Okay. Well, then the non-flutter design principle is simply an hypothesis that this classical flutter can be avoided by reducing the torsional lateral frequency considerably compared to traditional bridge design. So when I started doing my first wind tunnel tests of a sharp-edged rectangular cross-section having a width to height ratio of 10, we observed that this non-flutter design principle performed very well because flutter did not occur. And it was simply avoided by switching the torsional and vertical frequency, and it was done so by increasing the mass moment of inertia. But first time we tried to kind of publish these results, one of the reviewers did not understand how this was possible because this particular cross-section was known to be prone to torsional flutter. And we did not observe any flutter at all, but in his mind, the section should have become unstable in pure torsional motion. So since that did not occur in our test, kind of went into depth with that. I'll come back to that. But the reason why he had this opinion was probably because that the literature is rich on reports on positive A2 star values of this kind of section, but much of that is based on harmonic forced motion tests. And A2 star is basically a function describing the torsional aerodynamic damping due to harmonic torsional motion. But there exist several other functions describing the aerodynamic stiffness and damping due to the motion of the section in vertical, torsional, and lateral degrees of freedom. All these functions are referred to as flutter derivatives or aerodynamic derivatives. These derivatives are usually obtained by wind tunnel tests and identified using system identification methods. So, in order to explain how torsional flutter was avoided in our test, we have to deal with the system identification methods being used and try to enhance them in order to minimize the residual and optimize our model fit to the test. So I did a little bit of development on how to use these methods, and that is also covered in this thesis. But the main work is mainly the development of a bridge deck where low torsional natural frequency can be obtained without sacrificing the stiffness in the torsional degree of freedom. This includes several rounds of wind tunnel studies of triple box cross sections. When we say a triple box section, it means basically that we have 3 boxes that is mechanically interconnected, and it consists of 3 separated bridge decks, but they are kind of widely separated, so so the flow can go can go cross it in the, if you have 3 decks, one here, one here, one here, the flow can go like this, and no, it's only 3 decks. The results of these wind tunnel tests showed that aerodynamic stability was obtained up to 88 meters per second in full scale, despite of a really low mass distribution. And this stability was obtained even at torsional to vertical frequency ratios as low as 1.03, but it performed better at frequency ratios that was slightly higher, like 1.20. At frequency ratios equal to 0.97, we did see vortex shedding with large amplitudes.
Excuse me, Michael?
Yeah.
Are you showing the full presentation? We can only see the front page.
Yeah, I will come to that.
Okay, thanks.
So during my research, I met a lot of skepticism on reducing the torsional frequency, because that is actually the opposite of what has been recommended since the collapse of the Comuneros. Some people said that multimodal flutter would occur instead of classical flutter. Others said that torsional divergence would occur. One professor even called it for madness to reduce the torsional frequency. And dealing with these aeroelastic instabilities, we should introduce torsional divergency as a static instability problem occurring due to the second order effects of the quasi-steady aerodynamic moment on the section, which is quite similar to elastic stability problems of Euler columns, which is very known to civil engineers at least. And obviously, when we talk about the torsional stiffness of a bridge deck, it is very important for the stability. But we also have to remember that the natural frequency is simply the square root of the inertia compared simply the square root between the stiffness and the inertia. So yeah, it's not as simple as just a question about frequencies, high or low. In fact, it turns out that simple logic and conclusions drawn on linear theory is kind of not enough to understand this complex interaction between long-span bridges and high winds close to instability. That said, it's true that torsional stiffness of a long suspension bridge is essential. However, in order to make the torsional natural frequency lower than the vertical natural frequency, which was kind of the hypothesis on how to avoid flutter for flat plates or streamlined bridge decks, the torsional stiffness of the deck has to be very low. So we had to go down this road to study it. So in order to obtain a higher torsional stiffness with these kind of designs, we had to work with a wider separation of the main cables and a wider bridge deck, so to speak. So yeah. And finally, we found that lightweight bridge decks with low torsional natural frequency can be designed to be aerodynamically stable, even though the frequency ratios between 1.07 to 1.20. But yeah, the kind of sections that can be triggered to have such low frequency ratios is mainly twin and triple box girders with large separations between the bridge decks. And for these kind of sections, flutter turns out to be a minor problem because of high aerodynamic torsional damping associated with the A2 star derivative. And we found that the low frequency ratios did not necessarily turn to divergence, but on the other hand, we did also see that there's not any reason to kind of artificially reduce the frequency ratio for these kind of multi-box sections, because they perform very well against flutter even at frequency ratios of 1.20. So yeah, so let's move to slide number 2. I guess I already introduced the subject. The rest of the outline is basically a presentation of the main research question, and next what kind of methods I used to study that, and then I will dig a little bit deeper with the main findings. And finally, I will sum up and give the conclusions. Yeah. So there's a lot of wide fjords in, for instance, Norway, which should be crossed by very long span bridges or other kind of structures. And for these straits that is kind of longer than, say, 1.6 or 1.7 kilometers, we need to develop new technology in order to kind of cross them, or at least we know that the way we built bridges in the 60s and 70s and the last century, it may not be feasible for such long spans. So yeah, we're looking at other kind of designs involving 2 or 3 bridge decks in order to enhance the aerodynamic stability mainly. If we look at the flutter wind speed for a classical flat plate, and use the parameters for a bridge deck, the modal parameters, which kind of change with the span length, we will see that the flutter wind speed tends to decrease with the span length. So when we kind of try to solve the flutter wind speed for a flat plate at different frequency ratios, we'll see that it kind of increases with the frequency ratio, gamma omega, but at a certain level below 1.1 or 1.2, depending on the modal parameters, we will have no solution to the flutter wind speed. So much of my work has mainly been an exploration of what happened with the behavior of the different kind of bridge cross sections in that area. And the question I'm trying to answer is it possible to design a lightweight bridge deck that is aerodynamically stable by using this non-flutter design principle? And so what is the non-flutter design principle? Yeah, it's basically the hypothesis that flutter can be avoided by having a low torsional to vertical frequency ratio. But is it lower than 1? Is it lower than 1.1? Or is it lower than 1.2? It's a good question. If you look at the flutter curve, you see that there's no solution to the flutter wind speed below 1.1. So in that case, it would be 1.1. It's kind of an important question, because if you make it 0.7 or 0.8, you have to sacrifice a lot of torsional stiffness in order to go that low. But if you make it like 0.99, then you still have sacrificed some stiffness. But if you make it 1.1, then you might have enough torsional stiffness in order to get the stability you want. But so is that non-flutter? Is it non-flutter? I don't know. I've been studying the subject for 5 years, but I would say that it is, looking at this curve and looking at these traditional flutter curves where you see the asymptote of the flutter wind speed going towards infinity down there. But then again, on the other hand, this is just linear theory for a flat plate, and the aerodynamics of a bridge deck that is going to span 2 or 3 kilometers is far more complex than just a simple flat plate. So I'll shortly introduce the methods I've been using. If you have a simple suspension bridge, which is a word or a phrase that I think was introduced by Arne Seelberg, describing a suspension bridge having only a main span and then no backstays. We have a given mass and stiffness distribution of the bridge deck and the main cables, which gives us some input we can use in a static analysis. And when we have kind of reached the dead load situation where we have equilibrium, we can conduct a modal analysis to get the frequencies of the vertical and torsional modes, for instance. These modal parameters are used in the wind tunnel tests we're conducting of a given cross-sectional shape. And the interpretation and the data analysis of these tests tells us a lot about the performance of this kind of shape in the given condition that is going to operate. And finally, we can use the results from the wind tunnel test to conduct flutter analysis and static divergence analysis. Okay, for the static analysis, it's important to realize that these structures are very slender and they are very flexible. So the displacements of the bridge deck is important for the stiffness distribution in the main cables. It means that you have to kind of iterate through until you get the stresses in the dead load situation and thus the stiffness in this case. And if you're looking at the static analysis for the wind, you have to deal with maybe some nonlinear steady aerodynamic loads, which means that you have to solve the equilibrium step by step. And in some of the older textbooks, there's usually a formula for torsional divergence, which is based on the equivalent modal coordinates for pure torsional divergence, and this tends to be wrong and can seriously overestimate the static stability limit, because it relies on a linearization of a highly nonlinear problem when we talk about long-span suspension bridges. So instead, you should use a finite element approach and use Newton-Raphson iterations to kind of get the displacements step by step. Yeah, you can see the convergence criteria for these Newton-Raphson iterations. When do you kind of when are you satisfied with your with the displacements you have obtained during your finite element analysis is basically defined by a sum of it's defined by the sum of differences between the last steps. So when you kind of reach your convergence criteria, it's at the point where the Euclidean norm is below some level which you kind of define in your analysis. It has to be, you have to reach convergence in order to move on with the aerostatic analysis. When dealing with the modal analysis, we're kind of obtaining the mass and the stiffness distribution in the dead load situation, and then we solve the eigenvalue problem, which gives us the eigenvalues and the mode shapes. Okay. The wind tunnel tests are conducted for the cross section using different methods. The input to the static analysis is done by having static tests, where basically measure the forces on the section and normalize it with some geometric parameter of the section. Then you can do free vibration tests, which is a simulation of the full-scale bridge deck in a model scale, where you kind of reduce the mass and stiffness properties of your finite element model to 2D or 3D setup in the tunnel, and then you kind of look at the wind and structure interaction in model scale and light, and you can play around with the parameters and study what this means. And finally, you can do forced motion tests. I've been working with harmonic forced motion tests of the section, which is used to give the aerodynamic derivatives. You can get the aerodynamic derivatives by free vibration test as well. I will get into that later. On the flutter analysis, you basically have three different kind of flutter. You have torsional flutter, which is mainly related to A2 star. It's also called for single degree of freedom torsional flutter, because it only involves 1 degree of freedom in order to occur. It may occur if A2 star is positive in the sense that it gives you negative damping when the wind speed increases. Then we have classical flutter, or 2 degree freedom couple flutter, which is stiffness driven and related to the loss of torsional stiffness in wind, which is what we might avoid if we switch the torsional and vertical frequency. Or that is, we can avoid that if we do that. In this case, the structural damping is not really important, which it is for the torsional flutter. And then of course there's multi-degree of freedom, where the interaction of several modes can in some cases give lower flutter wind speeds, or can maybe also describe the real flutter behavior better. But in the work I've done, it did not turn out to be extremely important, in the sense that the critical flutter wind speeds were not reduced by using more than the two lowest vertical and torsional modes. So, and you can see the equations of motions we're trying to solve. We have a mass matrix, a damping matrix, stiffness matrix, and then we also have an aerodynamic damping matrix and an aerodynamic stiffness matrix, and they kind of depend on frequency and wind speed. Right. So let's move on to the main findings, which is included in my thesis. Okay. First paper in the thesis includes a study on the influence of span length on the torsional to vertical frequency ratio for a simple suspension bridge. And I don't know if you can see it in this presentation, but if you look at the curve to the left top, you can see the span length on the x-axis, and you can see 4 different cases of simple suspension bridges. And then we basically solve the eigenvalue problem at different span length, and we find that the torsional to vertical frequency naturally goes towards a lower level when the span length increases. So it becomes more and more relevant how these kind of sections perform at low torsional to vertical frequency ratios. So when we increase the span length. And then if we look at the top right plot, we'll see how, for the same cases, what is the critical flutter wind speed for these. And we also see that they kind of decline with the span length. This paper includes wind tunnel tests of 4 different sections: a bluff, sharp edges 1 to 10 section, and a more kind of a flat plate, and then 2 different kind of twin box sections. And we also see that the flutter wind speed is increased if we have a twin box, and if we increase the separation between the boxes, the flutter wind speed increases even more. Okay. One of the results from this paper is that the flutter was avoided for this rectangular section with a side to depth ratio of 10. So flutter was avoided when we had a lower torsional frequency than vertical. And why is that? Why is that when the literature reports that A2 star is positive, which should mean that the frequency ratio is not important for the kind of flutter. So, but nevertheless, we did not see any flutter. So that was a question we had to try to answer. And in order to do that, we did study all the tests we done on that section in depth. We did 5 tests at each reduced wind speed, and we tested it at 4 different torsional to vertical frequency ratio in the same section. And we tried to find the aerodynamic derivatives for all these 3 decays. By doing so, it did not turn out to be simple task because there can be a lot of variance in the results you get from classical system identification methods. So we had to basically try to enhance the use of these methods in order to get more reliable predictions of the flooded derivatives. And for instance, if you use a covariance-driven system identification method, we kind of found out that the results were depending a lot on the number of time lags you're using in the block-Hankel matrices. On the other hand, if we're using a iterative method, for instance, the iterative least squares method, it could turn out that it would not converge. But if we use a method called the modified unifying least squares method and combined it with a covariance-driven method, the covariance block-Hankel matrix method, we used actually, and we kind of tried to optimize the number of time lags used in the covariance-driven system identification method. And if we optimize that and used that as our best initial guess in the unifying least squares method, we were able to kind of enhance the model fit to our measured signals, which made it possible for us to find flooded derivatives up to reduced frequencies of the wind speed divided by the frequencies by times the width of the section, and the frequency in radians per second is equal to 10, which is quite high actually. And we even found the flooded derivatives after the occurrence of flutter. So another thing we got from the system identification was kind of a possibility to track the development of the mode shapes of the section in wind. And we see that the vertical mode, so to speak, does not really change with the wind speed, but the mode that is purely torsional in still air becomes a mixed mode of torsional and vertical motion as the wind speed increases. Another thing we found was that if we have a time history with a free decay, we could kind of split it in several, and we could look at what kind of flooded derivatives do we identify at different portions of the free decay, having different amplitudes. And we could see, for instance, for A2 that if we wait a little bit until the amplitude is lower, we will get negative A2, so to speak, at the low wind speeds, while if we estimate A2 star in the start of the signal, it is positive. So that it kind of indicates that there are some non-linearities of the aeroelastic behavior of this cross-section. But the main findings is basically the results for A2 star, because it turns out that in the literature there's some results for A2 star based on forced motion tests, which gives us positive A2 star values. But when we kind of estimate the flooded derivatives at higher wind speeds, we get negative values, and that kind of explains why we did not see torsional flutter in the test we did. Also kind of kind of support the findings we did in paper 1. So that's kind of interesting. We have agreement with the literature, so to speak, that we have positive A2 star values at low reduced wind speeds. But as soon as the wind speed gets higher, the slope turns, and finally we get negative A2 star. It's kind of interesting. We also used these results to study some of the implied approximation that is used when dealing with flutter derivatives based on free vibration tests. Because we have to remember that the flutter routines that is commonly used within civil engineering and for bridge aerodynamics goes back to the 30s, so to speak, where these flat plate studies were conducted for wings, for airfoils, and they rely on parameters or aerodynamic derivatives, if we call it that, which is functions of harmonic motion, which is only valid at the flutter wind speed. It's not valid before and it's not valid after, so to speak. So when we kind of write the equation of motion the way we do, and we use it before the flutter wind speed occurs, it's really speaking not the same, because we don't have harmonic motion, and we also have to question what kind of frequency do we use. As if you look at the equation of motion, there's only one frequency, and that's because in the flutter routines there's only one frequency at the critical flutter wind speed, which is the flutter frequency, which is the one you're searching for. But when you do the free vibration tests before flutter, we have several frequencies. We have a vertical frequency of the vertical mode. If we go back, this modes which kind of keep the mode shape constant, and then we have a frequency for a mode shape which becomes more and more coupled. The mode that was purely torsional and still air. So what kind of frequency do you use to define H1 and A2 or A3 and A4 in the calculations? That's kind of important. So therefore I tried to do the flutter routine using two frequencies, the same frequency which was used in the estimation of the free vibration flutter derivatives, and then I compared it with using only one frequency. It could be the flutter frequency, it could be, so to speak, and found that even though you use two different frequencies and then you kind of go through it, it gives only a deviation of 3, 4, 5% on the flutter wind speed in the end. So this kind of implied approximation that is used for the free vibration flutter derivatives seems to be okay within these limits. Yeah. So to sum up on paper 1 and 2, the reason we did not see torsional flutter was mainly because A2 star turns out to become negative at higher reduced wind speeds. It doesn't mean that torsional flutter cannot occur for a sharp-edged cross section with a side ratio of 10, but when it has the mass properties as the one we tested has, it will be able to withstand torsional flutter, even though A2 star is positive at the low reduced wind speeds, and then A2 star turns sign to negative at higher wind speed, which makes it even more damped and more stable. And then So we can also say that these implied approximations that is used for the free vibration flutter derivatives seems to be a reasonable approximation to determine the flutter wind speed. I will not deal with paper 3 and 4 in my thesis in this presentation, but I will move on to the last paper that was included in the thesis, which deals with this triple box girder that I tried to develop during my PhD study. And here you see a cross-section where we have a central box, which is quite narrow, and then we have the two external boxes quite far away from the central box. The reason why it looks like that is in order to make the torsional frequency low and still have a high torsional stiffness, we want to have a wide separation of the main cables, and also we need to have a lot of mass that is even more eccentric than the main cables. It means basically that the radius of duration of this kind of section needs to be larger than the main cable semi-distance, so to speak. So we have to have mass outside of the main cables in order to make the torsional to vertical frequency ratio lower than 1, and that is basically the main practical challenge in doing a non-flutter design. But nevertheless, this is possible. So for this cross-section, we studied both the situation where we had fairings on the central box and a situation with sharp edges. So as we saw in paper 2, we know that sharp-edged boxes having a side ratio less than 10 might be prone to torsional flutter. I mean, we did not show that in paper 2. It's kind of, but it's Matsumoto showed that in one of his papers, in which is basically he gave the results that we were for the BD10, the section with a side ratio of 10, which we were kind of benchmarking our test widths or comparing our test width in paper 2. But he showed that that rectangular sections with a side ratio equal to or less than 10 would be prone to torsional flutter. So the first section we did tried to actually use a sharp-edged cross section with a side ratio of 6 approximately, and then we add these external boxes, which I believe will give torsional aerodynamic damping. So it was kind of to study that, but these sharp edges turns out to really generate a lot of vorticity, which makes the section more prone to vertex-induced vibrations. So we added the fairings later on. So this setup with the fairings we're calling test series 9, and the setup with the sharp-edged central box, we call it test series 8. And it means that we have tested 9 different cross sections during this research period, including my master thesis, where we started doing the BD10 tests. So for series 8 and series 9 here, the final section I worked with, we have the steady force coefficient, or the static force coefficients of these two sections. And we see that basically that the moment slope, the red one here, is absolutely flat, or close to flat at least. I mean, it's not absolutely flat, but it's really, really flat. But if you look at it, it's negative at 0 degrees angles of attack, which means that it will turn in the counterclockwise direction, going with the nose down to the wind. And then if you kind of zoomed in on it and you look at how it develops up till -6 degrees angle of attack, it becomes less and less. So we're having a negative CM slope, but with some small non-linearities. And we also see that the lift is negative, so the wind will kind of pull the section down. And actually this is a really good thing for static divergence, because when the wind is kind of pulling the section down, the tension in the main cables will increase, which makes the stiffness more stiff, and thus these second order effects that is normally causing static divergence or torsional divergence, they're not a problem for this section, or for any sections having these kind of properties. Also, we found aerodynamic derivatives for this section, and they're reported in the paper. You can maybe see them here also. We're having the derivatives for test series 8 at 2 different angles of attack. We can see, for instance, that A2 star is negative for this section, even though it has a central box with sharp edges and a side ratio of 6 only. So it must be the external boxes introducing this torsional aerodynamic damping. Yeah, and then we also see, maybe you cannot see it on the slides, but you can see it in the paper that the derivatives depends on the angle of attack, and it's not something kind of I discovered. It's widely well known in the literature, but it's really, really important for the flutter analysis we are conducting. So that's why I want to stress it. Okay. I started this bridge having several different configuration of torsional stiffness, and the stiffness was mainly adjusted by separations of the main cables, giving a wide range of torsional to vertical frequency ratios. And if we look at the standard deviations in the vertical and the torsional direction during the free vibration tests, we see that when the torsional stiffness is too low, we will have vortex shedding indicated by the peak here in the bottom 2 plots. But we also see that the section has a really, really high torsional aerodynamic damping. At high wind speeds, it's almost impossible to excite the bridge. It has a very, very high damping, so it's really, really good against flutter. Compared to a flat plate, the flutter wind speeds are approximately 2 times as high, and using the derivatives obtained from the force motion tests, we do not get flutter curves having an asymptote similar to the flat plate. And if we kind of use these derivatives to predict the frequency and damping in wind, we will get estimates that agrees with the parameters identified by system identification until reduced wind speeds of 5, but at higher wind speeds we get disagreeing results, which may be caused by the static rotation of the section, which again underlines that the behavior of this kind of section is highly nonlinear. Yeah. What else can we say? Yeah, the wind tunnel test showed that it was possible to get aerodynamic stability despite that the bridge girder is very, very light, and it was also confirmed by the finite element tests. And yeah, then I just want to kind of sum up and give my recommendation in answering the research question that I posed in the beginning of the presentation. And the question was basically, is it possible to design a bridge deck that is lightweight and aerodynamic stable by using the non-flutter design principle? And yeah, we have the question here, and here comes the answer. And the answer is that it depends. It's possible, but it is definitely not necessary to artificially reduce the torsional stiffness to do so. In order to go there and design a cross section that is that has high enough torsional stiffness and has a low torsional frequency, you have to create a very special kind of cross section using 2 or 3 section, and for these with a wide separation. And for these kind of section, flutter is not a problem due to the very, very high aerodynamic properties. They're very, very good aerodynamic properties. So yeah, since flutter is not a problem for these kind of sections, even the frequency ratio is only slightly above 1, then there's absolutely no reason to reduce the stiffness to avoid flutter. And also the static response is much better when the torsional stiffness is high. So that is the conclusion on this research question. Yeah. All right. Thank you for listening, and if you have any questions, please let me know.
Yes. Thank you, Michael. That was a very interesting introduction and presentation. Does anyone have any questions for Michael?
Yes, I have a couple of questions.
Mm-hmm.
My name is Kjell Hava Belsvik, and I'm working with a suspension bridge in between other tasks, crossing the smaller crossing Langenuen. It's about 1,250 meters main span. And I just wonder, when you call the bridge deck for a lightweight bridge deck, are you indicating special materials in the main deck?
No, I'm not really working with material science in this work or at all. I'm just kind of saying that the weight of the bridge deck is really, really important for the price of the structure totally, and then we can kind of, doing the wind tunnel test, we can test the sections in different mass configurations, and usually when the mass gets low, we will have trouble with aerodynamic stability. But for this last section I tested here, it performed stable despite low mass.
Yeah. So if we, well, I could say we are having a kickoff on a special FOU project dealing with an aluminium material in the bridge deck.
You are?
Yeah, and also this is in the same the same questions that we have. You have also asked in this thesis.
Yeah.
So it will be very interesting to see how we can document stability, even though we have a lightweight bridge deck.
Yeah.
So maybe we will have a cooperation there. We'll see.
Yeah, it would be interesting.
I have also another question about the same. You indicated that it was a wind stabilized bridge deck. So the more wind you get, the more stable it gets. How is that possible?
Stable in the dynamic sense, so to speak.
Yeah.
And simply because the interaction between the wind and the bridge deck it generates more and more damping the higher the wind speed gets. Of course, the pressure on the bridge due to the wind pressure increases with the wind speeds squared, so to speak, right? But and that will of course increase the static displacements and the static deformations. That is how that is. But a suspension bridge has a non-linear stiffness behavior, you know, and it's highly depends on the tension in the main cables. So if you kind of loosen the tension in the main cables by, for instance, if you have high wind speeds and a positive lift, it means that the wind goes in and actually lifts up the bridge deck, which reduces the tension in the main cables and thus also the stiffness of the structure, which is some negative second order effects in the structure. But if the lift is negative and you're actually pulling the bridge deck down, you increase the tension in the main cables and thus the stiffness, and you have some, you might say you have positive second order effects but of course in that case you have to really focus on not exceeding the limit of the cables, the limit of the stress allowed in the cables. Does it answer your question? Or?
Yes, as far as we can go today, I think it's a good question, a good answer. Yes, thank you.
Good. Thanks.
Does anyone else have any questions for Michael? No, no questions. Okay, then I think we'll end the recording. And thank you again, Michael, for a very interesting presentation.
Thank
Yeah,
you too.
Yeah. The next webinar from the Coastal Highway Route project will be next Friday. Sorry, no, in 2 weeks. It's on Friday, October the 19th at 10 o'clock, and it will be by Renny Arismendi and his project, Risk-Based Maintenance Optimization and Structural Reliability. So I hope you all return and log on to follow the webinar on the 19th of October. So thanks again, everyone, and bye for now.